You already hear me well, right? Okay, hold it like this. Okay, welcome to today's talk. Thank you first of all, to Maria helping us organize this talk and making it happen. My name is Utku. I'm data scientist under Giga project of UNICEF. Today, I'll be talking a lot about geospatial data. Hopefully, you're either familiar or working with people who deal with geospatial data, so it won't sound completely out of context. And I'll mainly be talking about, first of all, a lot of geospatial data that we use in our projects, also a little bit about Giga, what we do, and in general how we deal with geospatial data in our team, which is, I'm in applied science team. And today's topic is GigaSpatial, which is the framework that we introduced and made it open source in our team, which is like a scalable data engineering framework around geospatial data. And yeah, if you're ready, I can start. So first of all, let me introduce you Giga. Giga is a global initiative by UNICEF and ITU. It aims to connect every school in the world to the internet. And we have two offices, one in Geneva and one in Barcelona. I'm based in Barcelona. In Barcelona, we have basically it's a tech hub for Giga. We're building open source tech tools and also services to help governments to connect children, schools to the internet. And GigaSpatial, which is the main topic of today, is one of those tools, which helps us to kind of bridge the gap. And recently, like this year, we kind of rebranded as Digital Inclusion under Digital Impact Division, which is located in Valencia. And on top of school, kind of our area of research or like apply our services extended to health facilities and other delivery points or emergencies, bunch of other services that can affect children. So we are actually not just Giga now, we are kind of digital inclusion, which aims on a larger purpose. But most of the example that I'll give today will be around schools, but again, can be applied on many contexts that you'll see when I will be presenting. So, if you look at the agenda, I'll start with the challenges that we faced around geospatial data in our work, then move to introducing GigaSpatial, how it's born and what it's about, and then dive a little bit into architecture, and then give some use cases that we use GigaSpatial in our work, and then, of course, in today's world, I think there is no presentation without not mentioning AI. So I'll try to also include that to keep the tradition, and I'll talk about a little bit on AI rhythms. So, first of all, the challenge is if you work with geospatial data, or if you use it somehow, that you know that this geospatial data comes from very different sources. This is very fragmented. It can be coming from, for us, it can be coming from governments, sometimes from open source, communities like OSM and Overture. It can be provided by different companies as well, made open source as well, or kept private. And this is just one challenge here, is to kind of to find the source for the data that you need, and then of course this opens up next questions on how this data provided. For example, it might be provided as a PDF from a government, or CSVs or GeoJSONs, shapefiles, like which brings like another step that you need to succeed to kind of start it before you start using this data. And then let's say even you are familiar with the formats like of the data source, and you're okay with everything, then of course the challenge is not finishing there, and we have like you might be seeing like different resolutions than you expected, or like it might be in different scale. You might not find the data that you're looking for in terms of, like, for example, if you're looking for, let's say, data for one country, and then maybe for that source it doesn't even exist, or also like data might have some like faults inside, like it might have duplicates or like inverse geometries that you need to handle. So all of this kind of problems one by one that you need to deal with kind of brought us to the point that we had to spend a lot of time figuring out how to plug in this data into our kind of workflows. And we've seen that in kind of many domains, and we decided that we need like a standardized ways of doing, like, managing this data. And we've seen that this in like many areas, many domains, kind of like when we were doing climate applications, or like infrastructure planning, or like managing health services. Like, we've seen that we are using this data and we're facing these challenges again and again. And like we were spending a lot of time, of course, on this just to put this data into our workflows, like our models, our applications, even just the simple dashboards. This data is not just going to work when you just take it and drop and plug it in. You should have like some process before, of course, and which was counting most of the time, of course, to bring this data to the format that we need. And we wanted to eliminate this basically slow, sometimes even inaccurate, because if you write a script and you want to run it for multiple purposes of scripts, sometimes results inaccurate. Also reproducible, because we ended up having tons of scripts for each country or each different, like each data set. Then it's hard to go back, find it, when did you do the analysis, and which parameters you used, which resampling technique you use. So it was hard to kind of reproduce results for different cases, different timelines, or different kind of geolocations. So there kind of where we decided to kind of standardize our pipelines, because we are working on multiple domains, and also we are using like many different geospatial sources. Also, we are sure that many other people not in our areas, maybe for example like urban planning, are using like this type of sources. So we thought we can standardize first of all for us, and then make it open source so people can contribute and also start using this to kind of go faster in their kind of projects that require geospatial data. So we decided to build all kind of data engineering pipeline, we can say, or like a framework in Python as like an open source Python library at the end, which will help us manage collecting data from different sources and processing and standardization. So if you look at this simple like research lifecycle, it would help us mainly on the collecting and processing and standardization of the data. In our research cases, this was most of the time that we spent, and then it would help us to kind of focus on the other parts, which are mainly actual research parts, which is analysis and modeling, rather than focusing on the kind of connecting the data to your analysis. So the way we design develop this package to not to just to be an API, but also be kind of like a helper for you to build your own Geospatial database. So, internally at Giga, we work with medallion architecture in our dataset, which are mainly Geospatial. So we use 3 layers, if you're familiar with, like bronze, silver, and gold. With GigaSpatial, we added like one more layer to this view. I'll come to that later. But if you don't know, like bronze, silver, and gold, so just to summarize, bronze is basically how the data is provided, directly put it into storage, as in the raw format, whether it is PDF or CSV. And then silver, if you have done some processing like checks, for example, if it's data provided from a country, if it's actually in the country, if it has duplicates, if it has some other problems, and if you do those checks, this becomes, and write again, of course, to your directory, this becomes silver. Then if you have your schemas, your basically validations for your own models or your applications, then this data we process further, and then this data becomes gold. And then we introduce view layer with GigaSpatial, which basically mainly uses silver or gold data and generated through spatial joins, zonal aggregations, and resampling, in summary, and kind of gives us access in this data in different ways and resolution, which I'm coming in the next slide. So view layer is basically, you can consider it gives access to data in different ways. So for example, let's say here example is the shelter data. You might be, for example, mapping this shelter data directly to points that you have. For example, each school, you might be mapping directly nearest distance to shelter, which you'll see on the top left. Let's say it doesn't color it by distance, but yeah, that's point data. On the right, you will see that you might be mapping this data to school, let's say, school zones. You might define school zone as like a 1 kilometer area around the school point, like 5 kilometer, and you might be mapping how many shelters in the school area or not, which is like custom defined polygons, if you can consider that. And then the third one, you might be mapping this to admin areas here, which is basically administrative boundaries defined by the country. It can be different, can be representing different things, of course, from country to country, but which is one way of representing this data, which governments might be using more of this way. And then the last one is you might be directly mapping this data into grids, different type of grids. And in that case, of course, you might be using different resolutions, either if you have squares, you might be focusing on 2.4 kilometer squares, 5 kilometer squares, or hexagons, depending on your choice. So for us, this was kind of giving us, first of all, especially the grid, was giving us multi-resolution access for the same data set mapped either, for example, for some data set, of course, depending on their mapping strategy, this can be, you can be averaging, summing up for population, for example, or averaging for something else, like relative wealth, or getting the, for example, sometimes max or mean, depending on your analysis. But you can still kind of generate a bunch of kind of features for your like prediction models, for example. And if you have this data set already in your hands, then when new projects comes up, or when you're gonna start like kind of running new analysis, then it gave us opportunity to just directly start from modeling phase instead of focusing on all the data pipeline. And since the data set that we use, like mainly like Geospatial, and it required this type of mapping, it helped us a lot. So we kept this, we introduced this like kind of layer, view tier to the medallion architecture. Also, in the grid systems, kind of it helps us to kind of move from one level to other. Also, it's easier to kind of index and also like aggregate to one higher level up, for example. And also, it helps us to keep multiple variables in the applies to all of the views you see here. Multiple variables to kind of one data set. So you have population, settlement model, let's say build surface, or like a flood risk, or a bunch of other variables. You can see at this kind of same square that and you kind of directly feed this into your, of course, multi-feature ML models, for example. Yeah. Then I'll move to architecture of the package, how kind of we design it in terms of software design wise. So we kind of built the package around four main modules. Here kind of everything starts at core because, as I said, we haven't like designed this as like just being an API, but more like for users to build their own geospatial database. So here we have I/O clients that's kind of helps us manage data storage, different type of data storages. Currently there is like ADLS, Snowflake support, of course local, and a couple of different databases and data lake integration here. And we have the kind of base class for users to kind of implement their own database schemas if they need to. And next to this I/O client, I/O clients are basically managing the data written and data needs to be read from the data storage. That's basically client managing that. Then the schemas is managing all the kind of entities that we generate through this data pipelines, which might be like mainly around point of interest entities, and also some like for example buildings or infrastructure entities such as fiber lines or cell towers. In our case, you will find like lots of examples of the entities that we found, and it's usually easier to have validated schemas for this type of data because the way that countries provide, or like the way we get this data was always different, so we introduced this class. But of course for some users this might not be that like relevant. And next one in the core is HTTP, which basically helps us to fetch the data, like send a request, which is pretty basic. And now we move to handlers and grids, which is like one of the important kind of modules here. So handlers we call kind of dataset connectors. So they're the way of kind of package to connect external sources. So basically, like if we're gonna get the data from NASA SRTM, there's a handler for that that's managing the whole external connection, whether if there's a key required or not, or there's specific configurations for each data. That's what handlers are doing, and there are of course many handlers for each data set. Almost there is a handler to do that, and then the grid module is basically helping us to generate the grid. Either, for example, you have a set of points, you want to get specific resolution, H3 hexagons, and then you'll use this probably in seconds. You'll get your hexes and then basically your polygons. Same applies to S2 and Mercator. Currently 3 types of grids supported here. And then we have processing module, which is mainly helper functions. Like it's not very in here it becomes like very not object oriented, but more like split functions into different kind of modules that kind of help us to either clean, process, or transform the data. On the Geo module, you'll find things like aggregate points to polygons, or aggregate polygons to polygons, or like simplified geometries. You project geometries, and many kind of geo-operation kind of processing helpers, kind of standard we standardized here. And the raster, you'll find a lot of raster-related functions, like merging rasters, projecting rasters, again, resampling rasters, sampling rasters with points, sampling rasters with polygons with specified statistic. So all of the kind of raster functionality included here. And then entity processor is kind of helping managing with schemas, and then the kind of cleaning the mainly point data for us in terms of duplicates, fixing geometries, again some reprojections or checking boundaries, checking if the point is in a boundary or not. And then we include some algorithms that we developed or used in the algorithm section. That's mainly around like graph algorithms that you can possibly use with either like a lot of lines, for example for road data, or a bunch of points. You can generate a couple of graphs to see if you can find connected paths or not. And on top of this, we have the generators module, which is kind of wrapping both handlers grid and processing together, which directly helps us to generate the views that we saw in previous slide. So for example, if we use like a zonal generator here, which will, let's say we want to generate H3 resolution 5 view, and we want to map directly like population. Then basically we use that H3 generator, and then we have helper methods for each data set, such as map population, map number of buildings, or map the settlement in this let's say hexagon. So then basically with a couple of lines, these generators help us to kind of directly attach the data, the different geospatial data sources to the grids. Or this, I'm giving an example on grid, but this can be your admin boundaries, or this can be your custom geometries, let's say. And then we have also POI generator, which helps us, again, attach things, not this time to zones, but rather to directly to points. This can be nearest distance to something, like the building, or fiber node, or you might be mapping 1 kilometer population around the school. In our case, I'm using schools, but of course this can be applied to many concepts. So the most important, as I said, I think here in this package is kind of handlers, because that's kind of how we connect external sources, and also how we add more sources and more capabilities to the package. That was the kind of more basically complicated part for us to kind of that we brainstorm on. And they are basically kind of the handlers are managing the whole, we thought about how we can make it easier for kind of developers and also for the users to interact, and developers to implement new handlers. And we kind of try to implement all the data orchestration in our orchestrator class, which is a base handler, let's say. So we have base classes for base class for each kind of each subclass that we introduce later, which are like sub data sets, of course, from different sources. And this base class has the whole data orchestration functionality, plus has 3 components, which is again has lots of helper functions for when you start to kind of integrate new data source. So these are basic config, which is very kind of can be very important here depending on your data source, because config kind of helps you to connect to the how the data provided. Let's say, for example, if the data provided through S3 bucket, then config should be getting you the S3 basically S3 hashes for you to kind of send the request, right? And for different data sets, it can be different, as you can imagine. Sometimes, for example, here you see Google example, which is just actually URLs, but the hard part is not hard, but more like complicated part is here is that the data provided in their own tiling system, which is S2, level 4, very large tiles, and it's basically config here, like in the base config layer, is going to help you to kind of help you, like a developer or user, to kind of resolve the geometry. Like, for example, if you're passing list of points, or if you're passing a country, or if you're passing a different geometry, it will help you to identify which tiles or which files actually you need to download. So that's where like in the config that happens. So it's gonna basically overlay your geometry on top of the dataset provided, and then find the necessary ones and bring you those URLs, plus also generate the paths that in the data store how it should be kept. And yeah, because of course, like if the data is provided also in as one file globally, that might be, then you might not need to do much here in the config, but that's not usually the case. It's sometimes just country files, sometimes usually actually it's provider's own tiling system, because data is usually huge, and either they provide country level or their own tiling system in these cases. And the next is downloader, let's say, which is more straightforward. Actually, I think the config is since it's the main connector to kind of provider, it's the most tricky part. The downloader is usually either downloader sending like a fetch request to API, or directly requesting from URL, just getting from S3 bucket. And then reader, basically, if the data is raster, it's kind of checking if the data is corrupted, if everything is fine, it's bringing. Same applies to other CSV or GeoParquet or GeoJSON files. So yeah, mainly if the user can implement the config part, the rest, most of the like orchestration handled by the base classes. So and then basically what you can do just to load the data is called a handler. You don't even need to ensure that data available. You can just load the data. You can pass a source. Source here can be anything geometrically available, like list of lines, list of points, list of geometries, or just a country code. And then you have a couple of parameters here to help you if you want to crop the data to source, because as I said, it might be coming in different tiling system. And if you want to ensure the data available or not, like if it needs to be downloaded, then if you set this through, it will download and download. Yeah. So with this kind of, we expected, like our expectation was to make easier to integrate like different sources, and at the end, like we integrated. Probably currently like more than 10, 15 sources, like different providers using the same base classes, and we also they received like several external or also internal PRs, like using the same architecture. So far, it seems to be working, but of course open to new contribution and comments. And I'll move to use case to be a little move away from the architecture and look at the fun stuff. So I'll give one of our own use cases. projects in Giga that we are doing also in Barcelona. One of the projects that we do is like mapping schools for the countries, because the countries usually, not usually, but companies might not know where their schools are, or if they might know maybe which area they are, or they might not have the exact locations. And for that case, we are helping them to find out. And to do that, we use deep learning and high resolution satellite imagery. But the trick is here is kind of getting your training set and of course the validation set to make sure you have a good model to run it for the country or most of the countries in some cases. So, and what we are using, that is a high resolution imagery that we get from Maxar, and these images are like 300 by 300 meters. So for a country, if you try to download, it's like it becomes like millions of images, and they're actually high resolution. So it takes a lot of time to just download just to download images, and imagine just feeding like the huge data set into your model. You usually have to kind of, either for the training sets we have to sample, and also for the, of course, the test set or like man running for the country, we need to downgrade the size or like kind of eliminate some of them in a smart way to kind of reduce the computational time. So what we do is like for the training set, we use like 3 different sources: the government data, if there is, OSM and Overture, and then to kind of reduce to like a complexity in the training set, we remove the duplicate points, and then the next thing is we filter out to uninhabited areas, which kind of helps us to understand actually which source, like which locations might be actually correct. So kind of consider this as like increasing the quality of the training set, because if you're pushing a data that's actually not schooled to your training set and labeling as a school, that won't help your models to learn, right? Now what we do is to kind of label them as uninhabited or inhabited. We use like 3 different data sets here, which is Google Buildings, Microsoft Buildings, which are also AI detected by a settlement model. No, sorry, not a classification model, but like a, how do I say it? Segmentation model. And then GeoSpatial built-up surface, another data set we use. And to kind of to do this mapping, we use GigaSpatial, and especially the view generator here around points. First, we'll load our schools, wherever like OSM, Overture, and let's say our own APIs or governments. And then basically we pass them to POI view generator, which then asks basically, can you map the buildings in this kind of image, like around the school area? Can you map the Google buildings and Microsoft buildings, and then at the end build surface? And with some thresholds, we identify kind of label at the end the schools as like inhabited, whether inhabited or uninhabited. And for the inhabited ones, we keep them in the training set, and then for the rest, we like mark them as like a no, and also keep it in the, some of them we keep it in the training set as like a negative examples for the model. And also, of course, when you, let's say we have a successful model, when we want to run it for the whole country and we want to find the schools, we are not going to run for the whole tiles that we have, because as I said, that's going to take ages for a model to predict billions of tiles. And in that case, we again apply the same filtering and then use only like tiles that making sense for the model to kind of do the binary classification, whether there is a school building inside or not. So this is kind of just one use case, how we use it, and it's kind of, for us to, like, it's only a couple of lines of code through this package to map 3 different data sets into one kind of geospatial data set we can directly use in our training. Our next topic is readiness of this package, whether I'll elaborate on how our plans are or what we are doing in terms of AI readiness at this point. So we slowly started integrating. This is mostly internal, not included in the public package yet. We're still testing. Slowly started integrating MCP tools around basically GigaSpatial capabilities. And on our tests, it was actually going better than expected, because I mean we are also like we recently started, and then we assumed like it's probably due to like all the classes and all the kind of data structures are standardized. It was kind of easy to kind of build tools around this, like the MCP tools around this, to kind of, for example, this can be just talking to AI and asking, can you bring for the schools in Rwanda and the ones that has less than 500 students in, or like 500 population. So you can kind of building tools were, first of all, it was easy because due to architecture and then the data store that we built through GigaSpatial, and then also through LLM with the agentic approach, I think it was easy for model to identify the tools and like also move through different handlers and run the operation. So of course this brings us to the point that we, like this, with the new data sources, this can be a huge like a geospatial rack that we can add like a multiple from different domains geospatial data into, and then basically feed it into like with different tools with different purposes. Of course, this can be extended and feed it into a tool that can tell you in like a complicated problems, or like when you do urban planning or infrastructure planning. This can be like a tool that can automate this type of task for you, or like help you to plan any kind of geospatial task. Coming to an end here. So I think where we started was, I think we were dealing a bunch of scripts before we built this data, like kind of to clean and process the geospatial data to feed it into our models. And like here you see also like a bunch of sources that we currently like implemented under GigaSpatial. That's just the sources under there. There could be like many data sets already available. And we assume that it's going to be very helpful for us, and it seemed to be is, and also we thought that it could be helpful for the public, because this data can be used in different domains and research. And yeah, that's why we decided to do, of course, this we built this as a package and made it open source so that people can use and also contribute. And we always, of course, happy to see contributions from different domains as well. And yeah. Thank you very much. Hope you enjoyed. Hope it wasn't too Geospatial. If you have any questions.
I have a non-technical question actually. In the beginning you were talking about shelters, and I was wondering what's the relevance of shelters for you in these samples?
We are not using shelters.
Ah,
no. In some.
But what do you mean by shelter?
That was just an example, but yeah, but it's not.
Do you mean
It's
like
for example.
houses or?
Yeah, I mean, I guess it can be in work cases, even it can be like hospitals or schools for the children to hide, kind of.
Okay.
But it can be defined differently. But that was just an example.
How much gigabytes of data? Like, do you have all those data downloaded all the time, or like do you download it as needed, or like how do you do the data? Because like you mentioned, like every pixel is like 1 meter or something like that. Must be like millions of disk space.
Yeah, for some data sets, I would say, for example, if you're downloading buildings for a whole huge country like Brazil, that would be a huge data. I don't know how many gigabytes currently in my head. But also, if you're dealing with that type of data in your day-to-day work, and you don't want to also download directly from the source all the time, also you don't know when it's server gonna go down. There might be emergency. So for the countries that we work with, we keep the data in our storage. We download it actually. But of course, like if you're an urban planner here in Spain or even in just Barcelona, you might be passing just to download the data. You don't need the whole data set, right? Might be passing just Barcelona geometry and downloading just the relevant parts, which also the package allows you to do. So for us, we keep gigabytes of data because we need to keep, but it's kind of very flexible for users to keep it or not. Currently, it doesn't have any it's not like on the fly API. So it downloads the data, writes your storage, and then works like that. But if of course if we move to a point that there are cloud agents, then all this stuff should be kind of all the views at least should kind of transformed into database that can be accessible through the API, I would say.
I'm not sure if I got that correctly, but when you showed the architecture, I mean the processing steps and also the generators in some way that are application dependent, right? So if I now don't want to map schools to satellite data, but something completely different in the geospatial domain, I would build my own processing modules and my own generator.
Not really, actually. They are
already like wrote so much
be
software, so much different.
Yeah, exactly. So let's say, I don't know, you want to map some close by schools to parks in Barcelona. There you will find a function in Giga to find the nearest some like kind of list of lines or like you might kind of this type of applications you can still do. Kind of we try to generalize as much as possible. On top of those generalized functions, of course, we have in our own pipelines running in our own bench. But this is the public phase is kind of generalized phase. There's nothing only for schools.
And then maybe building onto that, because you mentioned Copernicus and also had it in the slide. I mean, there's this Copernicus viewer right now. Like, I don't know if you know it. Like for remote sensing data mostly, I think.
Yeah.
How much would you say is this similar, or can it like is it, or how much, or how close are your approach and like what Copernicus is building right now and also developing? Or is it
currently we don't I mean, of course, we have our own views like generators, but we don't currently build things like, for example, global friction surface, which is like a whole research project around it, right? That you kind of measure what the walking distance of a person from one point to other point, every part of the world. So we don't do that. We don't in Giga generate a kind of our own kind of research data sets, to say. More like we generate views to kind of feed the models into for us to help kind of identify, for example, where the poverty is or where the connectivity missing, kind of those kind of views for help us to kind of feed into models, applications, or dashboards. And Copernicus is like one of the providers, right? We use, and we use a lot of data sets from them. That's a model, build surface you've seen, population as well. Sometimes we also compare it with world population. So there is no like comparison in terms of like we are not benchmarking against someone.
So where do I find this?
The
is
package?
this- yeah, is it like on GitHub or?
Yes,
like,
there is
okay, okay, I do see. Okay,
Yeah.
thank you.
Yeah, I think it's a year ongoing project. We started a year ago, roughly. It's currently, I think, almost kind of stable level for the current data sets that we kind of provide, like included. And the data sets that can, as I said, can vary from domain to domain. It can be used in multiple domains.
Do you know of other organizations using your library?
From our side, other parts of UNICEF, we know people are using on different topics, like it can be climate, mainly what we heard, or also emergencies. Also ITU is our partner. They are using like infrastructure planning in some parts, as I heard. I don't know the details, of course, but outside of that, we also we have around, so far I think around 16K downloads, but we don't know who are they. So it's open source.
Thank you.
That's all.